Hi everyone, welcome to topic 4.2, probability distributions. Here are the learning objectives. First I'm going to explain the characteristics of the normal distribution. Then we're going to talk about the standard normal table, the Z table. And lastly we're going to look at calculating and interpreting probabilities for a random variable that follow this normal distribution. First let's consider the properties of the normal distribution. It's symmetrical around the mean, median and mode, and I'll show you this on the next slide. It's bell-shaped, meaning that most values fall close to the mean and fewer are away from the mean. It closely approximates the population distribution for many random variables. Some of these variables will be discussed with slide 5. Lastly, understanding the properties of the normal distribution are important because the assumption of normality is necessary for much of hypothesis testing with quantitative methods, and so you need to know how to test for this. Here we go further into understanding the properties of the normal distribution curve. You can visually see on the slide this bell shape. Notice mu and how the distribution is symmetrical around this value. Also, technically, the tails of the distribution never touch the x-axis, that bottom axis, but in reality, this often happens at 6 standard deviations. Lastly, the distribution is completely described by the population mean, mu, and the population variance, sigma squared. Okay, so what random variables do you know follow a normal distribution? Well, the answer is so many. Here are some examples on the slide. We've got grades, travel time to uni, travel time to work, blood pressure measurements, weight, height, time taken to run 100 metres, size of things, income and so on. So let's take one of those. We've got IQ. So IQ we know has a mean of 100 and a standard deviation of 15. It's normally distributed because most people fall around that mean of 100 and fewer people are in the tails of the distribution, having very low IQ or very high IQ values. Okay, so here's an example of 3 industries and the age of employees within each industry. Let's compare the normal curves. Firstly, the bottom left on the slide, you can see industry A and B. They have the same standard deviation, but different means. One has a mean of 42 years and one has a mean of 36 years. So we can see that the shape of the distribution is the same because the standard deviation of 5 is the same, but there's just a shift to represent that different mean value. On the other side of the slide, you'll see we're comparing industry A and C. They have the same mean, and so therefore the distributions are overlaying, but the standard deviations are different, and that's why we see that different shape. The standard deviation for industry A is 5, and industry C has a standard deviation of 8, meaning the data is more spread out. From slide 5, we discussed many examples of variables that are likely to be normally distributed. As you can imagine, there are infinite combinations of mean and standard deviations for variables that follow a normal distribution. And thus, to calculate probabilities for normal distributions, we need to bring it to a common language by standardizing the values and therefore calculating a z-score. The formula for the z-score is shown on the slide, x take mu over sigma. Note, by standardizing our data, the mean becomes 0 and the standard deviation becomes 1. Therefore, our z-scores tell us how many standardized units our x value is away from the mean. A positive z indicates the value is higher than the mean, and a negative z value indicates that the x value is below the mean. The greater the number, the further away from the mean. The standard normal curve that is provided with your book, if you have a look in Appendix A, gives you cumulative probabilities. See the curve on the slide where the probability for less than z is given in the table, and so that area to the left of z is what's given. We know that the whole area under the curve adds to 1, so if we do want the probability beyond z, we simply need to go 1 subtract the number given in the book. Please note that as a result of standardizing the data, as I've said previously, the mean becomes 0 and the standard deviation is 1. So this means that z values less than the mean are negative and z values higher than the mean are positive. Here's an excerpt from your Appendix A. As you can see, there are 2 tables. There are tables for positive z values and for negative z values. As you can see, for positive z values, which are z values to the right of the mean, we use the table on the left, and for negative z values, which are values to the left of the mean, we use the table on the right. In this example, we have a Z value of 1.52. As shown, your table will give you the probability to the left of this value. To get the probability of a value equal or less than Z, we look up the positive Z values, we look down the left column to 1.5 and then across to get the second decimal place of 0.02. You should try this out with your tables. This should give you a probability value of 0.9357. If we want to know the probability of a Z value greater than 1.52, we would simply calculate 1 subtract 0.9357 to get 0.0643. You can see this on the slide. In this example, we want the probability of a Z value less than negative 1.96. This time we look at the Z values with negative Z values, the table with negative Z values. Look down to negative 1.9, then across to 0.06 and you'll get 0.0250. Okay, so in this example we want to determine the probability between two Z values, specifically negative 1.52 and 1.96. To do this, we calculate the probability for 1.96, then subtract this from the probability for negative 1.52 to get the probability value in between. You can see this on the slide. 0.9750 take 0.0643 gives us the final answer of 0.9107, which is the area in between. For this example, we use the table in reverse. That is, we are given a probability value and we need to find the associated Z value. So say we want to know what Z value corresponds to less than or equal to 68%. We look inside the standard normal tables and try to find a value closest to 0.6800. If you have a look, you'll find 0.6808. This is the closest value and it yields a Z value of 0.47. This could then be translated into an X value with the formula on the next slide. Here's the formula: X equals mu plus Z times sigma. One more thing to know about the standard normal curve is that there are certain probabilities that we observe with the shape of the distribution. Specifically, 68% of the data will fall plus or minus 1 standard deviation from the mean, 95% of the data will be contained within 2 standard deviations of the mean, and 99.7% of the data will be within 3 standard deviations of the mean. This is known as the empirical rule, or the 68-95-99.7 rule. Lastly, here's an example for you to work through. Assume scores on a management test are normally distributed with a mean of 72 and a standard deviation of 8. What is the probability that a student will score above 60%? So first we transform the X value to a Z value as shown in the formula. This yields a Z value of negative 1.5. It will be negative because the X value of 60 is less than the mean of 72, so it falls to the left of the mean if we think about the standard normal distribution. Now we use the tables to determine the probability value. This value is 0.0668. Because the question asked for the probability greater than 60%, we have another step to do where we calculate 1 subtract 0.0668 to get the final answer of 0.9332. Now if that makes sense, you're on your way, but maybe also do some of the additional exercises that we've provided. This slide and the next are just here to remind you of the standard normal tables in the back of your textbook in Appendix A. Please note that these will be available in the exam. These are for the negative Z values, and this one's for the positive Z values. Thank you.